In this video, we're gonna continue talking about chapter 18. So we're gonna go over chapter 18.3 and 18.4. In chapter 18.3, we will talk about the proton transfer and the Bronsted-Lowry acid-base definition. The earliest definition for acid-base was brought by Arrhenius. Right, so in his definition, the acid should contain a H in the formula and then yield a proton or hydronium ion when it dissolves in water. And for a base, the formula should contain an OH, and when dissociated in water, it will generate an OH hydroxide ion. But we know that this statement has limitations, right? We know some, for example, the base, right? So it could be a metal oxide, or it could be ammonia that contains no oxide or hydroxide, but it's still a base. Because of the limitation in the Arrhenius definition for acid and base, later on, two scientists whose last names are Bronsted and Lowry, they defined the acid and base. So in their definition, an acid is a compound which will donate a proton, and a base is a compound that will accept that proton. So based on their definition, a acid-base reaction is basically a proton transfer process, right? So the acid will donate the proton and the base will accept it. Let's look at a couple examples. In example A, we have hydrochloric acid, which is a strong acid, right? So it will dissolve or dissociate in water. So what's interesting is that in this case, instead of for water, instead of working as a solvent, it's also working as a base. Right? Why? Based on the definition, right? So if it's something that can accept a proton, we can call it a base. Right? And so in this case, when HCl dissociate in water, right? So it will donate this proton here, right? So because water has this oxygen that has two lone pairs on the oxygen, right? So this lone pair on the oxygen, it will accept that proton, right? Because proton is positive charge and the lone pair has a negative charge, right? So it will accept that proton. Then based on the definition, because it's a proton acceptor, so it is a base, right? So water in this case acting like a base, and the hydrochloric acid, it acts like acid, right? Because it's a proton donor. In example B, we have ammonia dissolving water. So in this case, water is actually acting like an acid. Why? Because it can donate that proton, right? And the ammonia will accept it because ammonia have this lone pair electrons on the nitrogen. Right? So this lone pair of electrons on the nitrogen will accept that proton from water. Right? So we say this ammonia is a base because it will accept that proton, and the water in this case is an acid because it donates a proton. In the system of Bronsted and Lowry acid and base, we also have something called conjugated acid and base. Right? So it's very easy to understand their definition. For example, if we have an acid-base reaction, so in this case, hydrogen sulfide is the acid, and ammonia is the base. Right, so after they react each other, right, so after this proton is transferred, we know that the proton should be transferred from the acid to the base, right? So this proton from the acid, right, will be transferred to the base, right, attached to the ammonia, the nitrogen in the ammonia. So we'll say that the after losing the proton, right, after the acid losing the proton, and it become this HS minus. Right, we said this HS minus is the conjugated base, right? Is the conjugated base of the acid, right? So we said this H H2S is the acid, and after losing the proton, right, it becomes the conjugated base. We said this is a conjugated acid and base pair, right? So H2S and HS minus is a conjugated acid and base pair, where HS minus is the conjugated base of the acid H2S. Right, so for the base ammonia, right, so because it's a proton acceptor, right, so after getting that proton, it becomes HN4 plus. So in this case, we said that this HN4 plus, which is the ammonium ion, is the conjugated acid, right? It's the conjugated acid of the base of the ammonia. Right, so in this case, the ammonia and the ammonium ion, right? So NH3 and the NH4 plus, they are a conjugated acid-base pair, where the ammonium NH4 is the conjugated acid of the base ammonia. And notice that, right, when the acid loses a proton, the charge always decreases by 1. And for the base, when it accepts this proton, the charge also increases by 1, right? Because proton has a positive charge. Right, so for acid, when it loses a positive proton, its charge becomes lower, and for the base, when it gains a proton, the charge increases higher. In this table, you see more examples of this conjugated acid and base pair. Right, so we have 6 acid-base reactions, or in this case, we can say proton transfer processes. Right, so you can see in all these reactions, we have a pair of 2 pairs, right, of conjugated acid and base pair. Right, for the acid, right, after losing the proton, it becomes the conjugated base. Right, so it becomes the conjugated base. So that's 1 pair. And for the base, right, after gaining the proton, it becomes the conjugated acid. So that's another pair. Now let's work on an example problem to help us practicing identify the conjugated acid-base pairs. Right, so we have 2 chemical equations, or 2 acid-base reactions. So now you can pause the video and try to see whether you can do this independently. Okay, so now let's look at the first reaction. So first, let's try to find the acid, right? So based on the definition, an acid donates a proton. So in this case, we have H2PO4 minus, right? So it becomes HPO4 2 minus. So if you compare these 2 species, you see that it loses a proton, right? So for the H2PO4, you have 2 protons, but for the HPO4 2 minus only have 1 proton. So this is the species that lose that proton or donate that proton. So we said the H2PO4 minus, it is the acid. So the product will be the conjugated base, right? So this is a conjugated acid and base pair. So because this is an acid, right? So we know for the other reactant it will be the base, right? So for the carbonate, it's a base, right? It's a base because it obtain or accept that proton, right? So from CO3 2 minus, it becomes HCO3 minus. Right, so this is the conjugated acid. Right, so this is the conjugated acid of the carbonate, which is the base. So we have 2 pairs, right? So this is 1 pair, and this is another pair. Right, for equation 2, right? So we have water and sulfite, right? Sulfite and generating hydroxide and bisulfite. Right, so in this case, first let's find which one is the acid. right? So again, acid is the one that donate a proton or lose a proton. So in this case, water will be the acid, right? Because water from H2O to OH minus, right? Its charge decreased by 1, it loses a proton. So hydroxide will be the conjugated base. Right, so this is the first pair. And for SO3 2 minus, it will be the base, right? Because it accepts the proton, right? So it is a base, and the HSO3 minus is its conjugated acid, right? So we have a second conjugated acid and base pair. Here's another practice problem. So if you know the answer, you can comment below, and I will reply your comment. Based on what you just saw in the previous slides, you have seen that for every acid and base reaction, we actually have two pairs of acids and base. So on the left-hand side of the reaction, we have one pair, and on the other side of the reaction, we have another pair of acid and base. So you may be wondering, if the system is not at equilibrium, which direction does the reaction proceed, or what's the direction of the net reaction? Right, because they're both acid-base reaction. So to determine the direction or the net direction of the reaction, we need to figure out which acid and which base is stronger than the other acid and base. So the rule of thumb is that a reaction will persist to a greater extent in the direction in which a stronger acid and stronger base form a weaker acid and weaker base. Right, so the reaction will prefer for stronger acid and base to produce weaker acid and base. Right, so in this case, right, so we have stronger acid and stronger base on the left, so we'll say the net reaction, right, will toward the right hand side, or toward the side of the weaker acid and base. And in the second reaction, right, we have a stronger acid and base pair on the right hand side, so the reaction will proceed to the left. So another way to determine the direction is looking at this Kc value for the net reaction. Right, so in the first example, because the Kc value is greater than 1, right, so meaning that the product concentration of the product, right, is greater than the concentration of the reactant, assuming they all have the same initial concentration, right, at the beginning. So that means the product of this weaker base and the acid, right, is greater than the product of the concentration of the stronger acid and stronger base, and that's why Kc is greater than 1. And so the reaction will proceed to the right. Right, in the second example, because the stronger acid and base on the right hand side, so the Kc will be less than 1. Here the Kc is the Kc value for the net reaction, right? So meaning that you have a same initial concentration for all of these species, right, in the initial condition, and the reaction happened before it reached equilibrium is the net reaction, and the Kc value of the net reaction will determine whether this reaction proceed to the left or right. Right? If it's greater than 1, that means it will proceed to the right. If it's less than 1, that means it will proceed to the left. In this slide, on the right hand side, you can see there's a figure, right? So it's a acid and base ladder, so it compares the relative strengths of all the commonly seen acid and the base. Right, so in the exam or in your homework, you can have this figure available, and in the exam, I will also provide this figure. So using this figure, you can actually determine, right, or compare the strengths of the acid and base. And to determine the direction of a acid-base reaction, you can also use this figure, right, using the rule that the stronger acid and the base will form the weaker acid and base. So to apply this figure, use this rule that a reaction will proceed to the right if an acid reacts with a base lower on the list. Right? So if you start with the acid and then let it react with the base that's lower, right, below it in this list, that means this reaction will proceed to the right. Right, so let's work on a couple example chemical reactions and determine the direction of this net reaction. Right, so again, in this case, we're going to assume that all the species have the same initial concentration. Right, so we want to determine the direction of this net reaction before it reaches the equilibrium. Right, so for equation 1, we have H2PO4 and the ammonia. Right, so generating ammonium and HPO42-. Okay, so first let's identify the acid and the base. Right, so in this case, because H2PO4 lose a proton, so it will be the acid. Right, so this will be the conjugated base. So I'm using same color here to save some time. Right, so ammonia will be the base, right, and the ammonium will be the conjugated acid. Right, so now let's find their location in this figure. Right, so H2PO4-, it is right here, and the base ammonia is right here, so it is below H2PO4. Right, that means the reaction will proceed to the right. Right, so it will proceed to the right. So that means this H2PO4 is a stronger acid, right? So this acid H2PO4- is a stronger acid than ammonium, than the conjugated acid, than ammonium, right? And then we can compare them, right? So ammonium is NH4 plus right here, right? So H4PO4- is higher, so it is a stronger acid, right? So that just proves that our answer is correct, right? So this reaction will proceed to the right. And for the second reaction, again, first let's identify which one is the acid, which one is the base. Right, so first, I think water is the acid, right? Because water is the one that donates that proton. So I'll say water is the acid, and the conjugated base is the hydroxide ion. So I say water is the acid, and the hydroxide is the conjugated base. So HS- will be the base, right? And the H2S is the conjugated acid, right, against a proton. So now let's compare the relative location in this figure. So let me erase the mark I left earlier. Right, so now for water it is here. Right, so and for the conjugated acid, oh no, let's look at the base, right? So for the base HS-, it is right here. Right, so actually the acid is lower than the base in this list. Right, so in that case, the direction of the net reaction will be toward left. Right, so let's confirm our result, right, by comparing the strengths of water with the acid and its conjugated acid. Right, so water is here, the conjugated acid H2S is here. Right, so In this list, we can see H2S is the stronger acid and the water is a weaker acid. Right, so this is a stronger acid. Right, so stronger acid, this is a weaker acid. Right, so we know that for the net reaction, it will go from the stronger acid to the weaker acid. So that just confirms our answer, right? So it will proceed to the left. In chapter 18.4, we're gonna practice on solving the problems involving a weak acid equilibrium. But here, we don't need to worry about strong acid and base, right? Because their reaction will almost complete to 100%, right? So here we'll only look at the equilibrium of a weak acid, and for the weak base, we can use a similar approach. The approach to solve this type of problem is very similar to what we have done in chapter 17 when we solve the equilibrium problems. So we have two types of equilibrium problems for the weak acid equilibrium. So first is finding the Ka using the given concentrations. Right, so in this example problem, we have this phenylacetic acid. Right, so it's basically an acidic group attached to a benzene ring. Right, so the question says if we add 0.12 molar of this acid in water, and the resulting pH at equilibrium is 2.62, and then it asks us to calculate the Ka value for this acid. So first, let's understand this question. So it means that we have water and we add this acid in water, and the initial amount of acid we add is equal to 0.12 molar. Right, so that's the initial concentration. So this acid will dissociate and generate some protons, right? So at equilibrium, right, so meaning that this dissociation of acids at equilibrium, we have a pH of 2.62. And then can we use this information to calculate the Ka value? And of course, right? So the approach for solving this type of problem is first we will write down this chemical reaction, right? So this dissociation process. So we have the acid and dissolve in water, right? So here water will be act like a base, right? So the proton is the conjugated acid, and this is the conjugated base. Right? Then we will write down the expression for Ka. Again, Ka is the dissociation constant of a acid, right? Because A representing this is the equilibrium constant for the acid, right? So when this acid dissociates in water, the equilibrium constant is Ka, right? So we have the concentration terms of the products divided by the concentration terms of the reactant. Notice water is not included here because in this case water is a pure liquid phase, right? So its activity is equal to 1, so we don't write it in this expression for Ka. Right, so if we want to calculate the Ka, we must know the equilibrium concentration, right, for this concentration terms, right, in this expression. Right, so then we can create our ICE table. So the initial concentration for the acid is 0.12, which is given, and the concentration of the products are 0 at the beginning. So based on the stoichiometry, because the coefficients are all equal to 1, we say the amount of this proton produced, which is equal to x, is also equal to the amount of this conjugated base produced. And the amount is equal to the amount consumed, right? So of the acid consumed. So that is negative x. So at equilibrium, the final concentration of the acid is 0.12 minus x, and the concentration for the ammonium and the conjugated base is x. Right, so we can solve for x using the pH, because the pH, right, remember from previous lecture, pH is equal to the negative log of the proton concentration, right? So in this case, we don't know the proton concentration. It is X, right? It is X, but we know the pH, right? The pH is 2.62, right? So that means the proton concentration is equal to 10 to the negative pH, right? So we can calculate this concentration of proton. So that is equal to X, right? So that will equal to X. So we can substitute the value for X and 0.12 minus X into this equation, and then calculate the Ka value. That's pretty straightforward. Right, so based on what we concluded in the previous slides, right, so when we calculate the Ka value, we can substitute these values, right? So this concentration is equal to X, right? So this is X times another X, right? But earlier, for the denominator, we said the equilibrium concentration is actually equal to the initial concentration, which is 0.12 minus X, right? So minus 2.4 times 10 to the negative 3. But in this case, we can actually simplify the math a little bit by making a couple assumptions. So first, we can make the assumption that the proton generated from the auto-ionization of water is negligible. Right, meaning that because we have proton generated from the dissociation of the acid, and we also have proton generated from the auto-ionization of water, right? So that's what we learned in chapter 18.2. So for this assumption, we can assume that amount, right, the amount generated from the auto-ionization of water is so small, right, compared to the amount of the proton generated from the acid, right? So we can ignore this term. So we said the total proton concentration in the system is equal or just equal to the amount generated from the acid. Right, so that's our first assumption. So now we can then justify this assumption, right? So because the for neutral water, the amount of proton, right, is 10 to the negative 7, and if we compare that concentration to the concentration generated from the acid, which we calculated in the previous slides, so the percent is very small, right? So its percent error is less than not percent error, the relative percentage is less than 5%. Right? So you compare the amount of proton generated from the water auto-ionization, right? It's much smaller than the amount of a proton generated from the acid. Right? So we say this is a valid assumption. Right? So the first assumption is valid. Right? So for the second assumption, we can say because this acid has a very small Ka value, right? So because a weak acid, right? So we assume it has a very small Ka value. So we said the amount dissociated, right? So very small, right? Remember, for a weak acid with a very small Ka value, the amount of dissociation is very small, or the extent of this dissociation is very small. So we will say this amount of this acid that have undergone the dissociation is almost negligible, right? So we can ignore this concentration here. So we'll say the equilibrium concentration, right, is almost or equal to the initial concentration because the amount rated is so small. So that's why instead of using 0.12 minus X, right, we will use the initial concentration directly, right? So we can calculate the Ka value, which is 4.8 times 10 to the negative 5. And then we have to justify this second assumption, right? So based on our calculation, right, the amount of this conjugated base, right, produced, or the amount of proton produced, right, that should be equal to the amount of the acid consumed, right? So that should be equal to the amount of the acid consumed or have undergone the dissociation. And if you compare this number, right, to its initial concentration, right, so the relative percentage is only 2%, right, which is less than 5%. So we can say this assumption is pretty valid, right, so it is justified. So instead of using 0.12 minus x, we can directly use 0.12, right? So that will make our calculation a little bit easier. The second type of problem is using the given Ka values to find the equilibrium concentration of this species, right, after the dissociation of the acid. So in this problem, we have propanoic acid, right? So we use HPR for short, and we know its Ka value, right? It is 1.3 times 10 to the negative 5, right? Which is a very small Ka value. So later you'll see that because it's small, we can make a couple assumptions. Right? So the question is that if what is the proton concentration and the pH if 0.1 molar of this acid is added in water? Right, so using the same approach, right? So first we write down this equation for this dissociation process. So HPR is the acid, right? So water acts like a base, and this is the conjugated acid, and this is a conjugated base. So Ka is going to be equal to the proton concentration times the concentration of the conjugated base divided by the concentration of the acid. They all should be at the equilibrium. And because the Ka is given, right, so we can let this concentration terms equal to the Ka value. So next, let's work on the ICE table. Right, so we know the initial concentration of the acid. The product, the concentration is 0. Again, because the stoichiometry suggests that all the coefficients are equal to 1, so the amount of the proton and the conjugated base produced, right, let's set that equal to x. So the amount of acid consumed is equal to minus x. So at the equilibrium, the concentration of the acid is 0.1 minus x, and the concentration of the proton and the conjugated base is plus x. Right, so we can rewrite this Ka using these concentration terms. Right, so we say Ka is going to be equal to the given value, right? It's equal to x, which is the concentration of the proton, right, times the x, which is the concentration of the conjugated base, and divided by the concentration of the acid at equilibrium. And in this case, instead of using 0.1 minus x, right, I've used 0.1 directly because I want to simplify my math by making some valid assumptions. Right, so in this case, the assumption I made is based on this very small Ka value. Right, because this Ka is very small, I'll say this x, right? So that means the extent of this dissociation is small. So this x is relatively very small compared to the initial concentration of the acid. Right, so we'll say for the equilibrium concentration of the acid, right? So which is 0.1 minus x, right? Because this x is small, so I will say it's almost same or equal to the initial concentration. Right, so instead of using 0.1 minus x on the denominator to represent the equilibrium concentration for the acid, I just use 0.1, right? Because x is so small, so the change is negligible. So by making this assumption, you can see my math becomes much easier, right? So I can solve for x, and x is 1.1 times 10 to the negative 3 molar. And so then I can find the pH, right? So that's the log of the concentration of the proton, so that pH is going to be equal to 2.96. So after you finish, remember you always need to justify it, right? You always need to justify your assumption, right? Your assumption is that the amount of this proton of this conjugated base generated, this X, right, is very small, right? So meaning that the amount of the acid dissociated is very small compared to the initial concentration. Right, so if you compare this X value here with the initial concentration, which is 0.1, right, so the relative percentage is only 1.1%, which is less than 5%. Right, so we said this assumption is justified. I already said it's a pretty valid assumption. Right, so I'm okay with this answer. Right, in case if this percentage is greater than 5%, right, so we can no longer use 0.1. We must use 0.1 minus X on the denominator. So far, all the example problems we have looked at contains the acid that only contain one proton, or we call it a monoprotic acid. We also know that there are acids that contain more than one proton, right? Sulfuric acid, H2SO4, right? And also phosphoric acid, H3PO4, and many others, right? So they have more than one proton, meaning that they can donate more than one proton when they dissociate in water. And for this type of acid, we call them polyprotic acid, right? Polyprotic acid. And for polyprotic acid, it's gonna have multiple Ka values, right? So based on the order, right? Based on the order of these protons given away, or the number of these protons given away, right? So for example, for phosphoric acid, it contains 3 protons, right? So it's H3PO4, meaning that it could donate 3 protons. So for the first proton to be donated, we can use this first reaction, right? So from H3PO4, and it donates the first proton, so it becomes H2PO4 minus. Right? So to differentiate the Ka value of the other dissociations or further dissociations, we use Ka1, Ka2, and Ka3, right? So for the first reaction, we have Ka1, right? So meaning that's the Ka value for the first proton, right, donated. So we write down this expression, right? We have this Ka value. And for this H2PO4 minus, right, it still contains 2 protons, right? So it's still able to donate proton. So for the second reaction here, we start with H2PO4, right? So it will donate another proton, so generating HPO4 2 minus. And for this equation, the Ka value will be written as Ka2, and it has a value equal to this. And notice that this Ka2 is much smaller than Ka1. Right, so for H2PO4, it still has 1 proton left, and it can still donate it to the base. Right, so for HPO4 2 minus, it will donate the last proton it has left, and generating this PO4 3 minus. And for this reaction, the Ka will be Ka3, and you can see the constant is 10 to the negative 13, right, which is much smaller. Right, so for a polyprotic acid, right, so the Ka values, Ka1 is always way greater than Ka2, and if there are only 2 protons, and if there are 3, the Ka2 will always be way greater than Ka3. Right, so it's pretty easy to understand, right? So for the first Ka1, right, so you start from a neutral molecule and to a negatively charged ion. So to donate this proton, the proton is positive charge, right? So a positive charged proton leaving a neutrally charged acid, right? So it won't take too much energy to do so. right? So, but for the second reaction and the third reaction, you are trying to take a positively charged proton away from a negatively charged ion, right? So it's no longer a neutral molecule, it's a negatively charged ion. So you're trying to take something positive away from something negative, right? So it's much harder to do so, and that's why the extent is much smaller, so you have a much lower Ka value. This table gives you the Ka values for some common polyprotic acid at room temperature. Right, so the number of Ka values is equal to the number of protons the acid contains. Similar to a monoprotic acid, we can also calculate the equilibrium concentration for a polyprotic acid using the given Ka values. Right, so in this example problem, we have ascorbic acid, which is also known as vitamin C. Right, in lab number 7, you're going to determine the concentration of vitamin C. So this acid is a diprotic acid, meaning that it can donate 2 protons when it dissolves in the water. Right, so the first equation here shows you the dissociation of this acid when the first proton is donated. Right, and for the second reaction, shows you the process of the donation of the second proton. So the Ka values are given in the problem, right? So we can express the Ka1, the Ka2 using these concentration terms. And then notice how small these Ka values are. Right? So again, because of these small Ka values, we can use a very similar approach and assumption as we did in the previous example problem. And that assumption will definitely help us, make the math easier. Right, so in this case, I'm gonna make 2 assumptions. So the first assumption I'm gonna make is that, because this Ka2 value is so small, it's so much smaller compared to Ka1 values, right? So meaning that the acid, the proton, so the proton generated in the second equation is gonna be much smaller than the proton generated in the first reaction. Right, so when this reaction is equilibrium, this whole system is at equilibrium, the proton concentration, so I will assume it all come from the dissociation of the acid, and because the proton generated in the second reaction is so small. Right, so I'll say the proton concentration generated from the first reaction is equal to the equilibrium concentration. So here this will be the equilibrium concentration of proton. And the second assumption I'm gonna make for the first reaction is that because its Ka1 value is so small, so it's 10 to the negative 5. So I'll say the X, so the extent of this reaction, or the X, the product generated, is also so small, so negligible. So I can say the initial concentration of the acid, which is 0.5, is almost identical to the equilibrium concentration, which is 0.5 minus X, by neglecting the X. So now we can use the ICE table to calculate the X, or the amount of this proton and the conjugated base after the first reaction. So we have the initial concentration is 0.05, and after the reaction reached equilibrium, the equilibrium concentration for the acid become 0.05 minus X. And then for the acid, for the proton under the conjugated base, the equilibrium concentration is equal to X. And based on my second assumption, because this x is small, right? Because the k value is small, right? So we change the denominator, right, from 0.05 minus x into 0.05 by itself. And for the concentration of the proton, right, we set equal to x by ignoring the amount of proton generated from the second reaction, right? So ignore the amount generated from the second reaction. So I will use x directly, right? So that's going to be x multiply x, so I have x squared on the numerator. So you can see the math become much easier, right? So because the k value is given here, so I can calculate x, which is equal to 7.1 times 10 to the negative 4. Right, so now I can justify my assumption using this number. Right, so first let's justify my first assumption. Right, so my first assumption suggests that this proton generated from the second reaction is so small compared to the proton generated from the first reaction. Right, so using the Ka2 value, right, so which is equal to the proton generated from the second reaction times the conjugated base in the second reaction, which is this, right, divided by the HASC minus, right, which is the reactant in the second reaction. And this is the Ka2 value. Right, so I can create another ICE table, right? So using this equation, I can solve for x. So x, which is the amount of proton generated from the second reaction, is equal to 6 times 10 to the negative 8. Right, so if you compare this concentration, right, with the concentration of acid generated, or concentration of the proton generated from the first reaction, which is 7.1 times 10 to the negative 4, right? So we have 10 to the negative 4 here. Here we have 10 to the negative 8, right? So this concentration is much smaller. So that means our first assumption is a valid assumption, right? And then for the percentage, we can use right, so this 0.6 times 10 to the negative 8 divided by 7.1 times 10 to the negative 4. Later you can find, I didn't do the calculation, but you can do it, and you're gonna see the percentage way less than 5%. And then I can justify my second assumption, right? So my second assumption is that this x value in the first reaction is much smaller compared to the initial concentration, right? So this x value is 7.1 times 10 to the negative 4, and the initial concentration is 0.05, right? So the relative percentage is 1.4, right? So which is less than 5%. So both of our assumptions are valid, are justified. Right, so we'll go with the number we calculate using these two assumptions. Then so we can say the concentration for the first species HASC minus, right, is equal to 7.1 times 10 to the negative 4. The question also asks us to calculate the concentration of this second conjugated base, right? So ASC2 minus. So to do that, we use the Ka2 value, right, from the second equation. So to calculate the concentration of this conjugated base, we can rewrite this whole equation. So move this unknown to the left hand side and move everything to the right hand side. Right, so this concentration of this second conjugated base is equal to K2 times the concentration of the first conjugated base divided by the concentration of proton in the system. Right, so again, the concentration of proton is not the concentration of proton generated from the second equation, right? It should be the concentration of the proton in the whole system, Based on our first assumption, it is the concentration generated from the first equation, right? So we use 7.1 times 10 to the negative 4. And for the K2 value which is given, and the concentration for the first conjugated base is also calculated, right, in the previous step. So we can calculate the concentration of the second conjugated base, right? So we can see it's a very small number, right? 5 times 10 to the negative 12 molar, which also kind of justified our assumption. So for homework, I have two problems for 18.3, right? For these two, you're gonna determine the conjugated acid and base pair, and also determine which side this net reaction is gonna precede, right? By comparing the relative strengths of the acid and the base. And the other two problem is for chapter 18.4. So you're gonna calculate the K value using the given concentrations, or calculating the equilibrium concentration using the K value. And they're both for monoprotic acid. Again, comment and like the video if you have any questions. Either ask me using the comments, or send me an email, or text me.